Welcome to this explainer. Today, we're decoding how to turn raw FireDancer validator metrics into a truly compelling architectural narrative. You know, in testnet environments, a FireDancer validator can process upwards of 1 million transactions per second. I mean, that is just a staggering, overwhelming fire hose of data. Turning the raw metrics from that fire hose into a story that actually makes sense isn't just a basic requirement. It's a genuine engineering superpower. If you're preparing for a major capstone presentation or honestly just trying to get your engineering stakeholders aligned on a budget, you already know that raw data alone completely falls flat. You need a story. So today we're going to bridge that gap between complex validator measurements and actionable, evidence-backed engineering priorities. Here's the blueprint we'll be following today. First up, moving from metrics to meaning. Then, we'll map out the two-lane factory. Third, diagnosing pipeline bottlenecks. Next, we'll break down 3 crucial optimization heuristics. And finally, we'll wrap up by crafting the ultimate stakeholder pitch. Let's just dive right in.
Section 1. From metrics to meaning. Translating isolated numbers.
So we often start with these fantastic but completely isolated data points. Like say you measure how reducing block ingestion latency, maybe by batching I/O operations, lowers your overall CPU wait time. Against a fixed hardware baseline, that pushes your TPS, your transactions per second, higher. That is a great concrete correlation. It makes perfect mechanical sense. But, and this is a big but, raw data without a narrative is honestly just noise. Let's be real here. Handing a project stakeholder a 50-row spreadsheet of raw CPU wait times is basically just a highly effective sleep aid. If you actually want to win over those stakeholders and properly prioritize engineering effort, you've got to transform those isolated technical tweaks or even regressions into a clear, unified efficiency narrative. You have to explain the why, not just the what.
And that brings us to the absolutely crucial concept of synthesis. Synthesis is what bridges the gap between what the validator is mechanically doing under the hood and where your engineering team should actually be spending their time and money. Think about an engineer who just reports to the team, hey, disk I/O is down 5%. Well, so what? That doesn't move the needle because there's zero context. A successful engineer synthesizes. They align data management behaviors, how quickly and cheaply the system moves state and transactions around, with consensus behaviors, which strictly dictate what work actually becomes finalized on the network. When you fuse these two sides into a single cohesive story, you elevate your presentation from a boring status report to a powerful tool that drives real, high-stakes operational decisions.
Section 2. The two-lane factory, the validator blueprint.
To really master this synthesis, we need a rock-solid mental model. So I want you to picture the FireDancer validator architecture as this massive, highly synchronized factory pipeline. Notice how cleanly the labor is divided into 2 distinct pathways here. Lane 1 is your upstream data management lane. Picture this as the heavy-duty conveyor belts of your factory, your raw material handlers. It is totally responsible for bulk ingestion, storage, caching, and I/O shaping. Then, passing the baton, we have Lane 2, the downstream consensus lane. Imagine this as your pristine, highly secure quality control stations. This is where the delicate assembly and validation happens, stuff like transaction ordering, cryptographic signature verification gating, network voting, and ultimate finalization. This 2-lane pipeline is literally the foundation for figuring out where a proposed optimization will actually buy you tangible value.
Section 3. Diagnosing pipeline bottlenecks. Reading the machine's symptoms.
Now, by watching how material piles up along our factory line, we can read the machine's symptoms and pinpoint exactly where things are breaking down. Let's look at 3 distinct scenarios. First, if your downstream consensus components are just sitting there totally idle, well, that's a glaring signal that your upstream supply chain is simply underperforming. It's starving the quality control workers. Second, imagine you've got this super aggressive upstream ingestion, but it's just dumping raw data onto an overwhelmed CPU-bound consensus worker. Maybe it's getting stuck on signature verification. At that point, any further tweaks to raw I/O upstream will yield absolutely zero returns. You're quite literally just piling more and more boxes in front of a locked door. Finally, what if your consensus progresses rapidly, but you observe high disk seek latency? That disk latency acts as a massive hidden tax on the whole system. It tells you that you need improved block buffering and local caching to smooth out those end-to-end delays. By analyzing these symptoms through our 2-lane model, we can isolate the exact source of the traffic jam.
But with both of these lanes constantly interacting and depending on each other, a critical question pops up. How do we definitively choose which lane to prioritize first? Getting this wrong carries a huge cost. If you misdiagnose the bottleneck, Your team could burn weeks or even months of expensive engineering time tweaking a system that gives you exactly zero net increase in throughput. It is not enough to just spot a bottleneck, you've got to empirically prove that fixing it is actually worth the engineering capital.
Section 4. 3 Optimization Heuristics, a rubric for engineering effort.
To answer that prioritization question with total confidence, we apply a strict operational rubric. This rubric weighs our potential efficiency gains against the harsh realities of implementation. You have to systematically walk through these 3 steps. Step 1. Compute the marginal improvement. In practice, this means asking exactly how much additional throughput does this specific change buy us, assuming our consensus rate stays exactly the same. Step 2. Compute coupling sensitivity. This one is vital. How quickly will downstream processing amplify or dampen the gains we just made upstream? I've literally seen teams celebrate a massive upstream ingestion gain only to watch it get completely swallowed by a downstream bottleneck in vote processing. The result? Zero actual improvement on the network. Ouch. Step 3. Estimate implementation friction. Basically, how invasive is this change to safety-critical code paths? A massive, complex rewrite of the consensus logic might theoretically offer a 2% gain, but the risk of introducing a consensus-breaking bug makes the implementation friction way too high. You might be far better off with a simple, safe upstream caching fix instead.
Section 5. Crafting the stakeholder pitch. Winning over the room.
Ultimately, combining this 2-lane factory model with our strict heuristics prepares you to draft the final synthesis note for your capstone presentation. Take a look at a pitch structured like the quote we have right here. Just listen to how perfectly engineered the sentence is. It explicitly names the target lane, data management. It quantifies the exact effect, reducing average block write latency by 18 milliseconds. Now, why does that 18 milliseconds matter to the people holding the purse strings? Because crucially, the pitch goes on to prove how the 2 subsystems are coupled. It explains that since consensus was previously CPU limited, this specific change reduced cube transactions for signature verification by 12%. When stakeholders hear about a 12% reduction in queued transactions yielding a tangible net throughput gain, they are going to nod their heads in agreement. This is exactly how you translate raw metrics into a compelling, undeniable engineering narrative. So, when you're putting together your own synthesis notes, treat these 4 elements as your ultimate checklist for success. 1. Map cause directly to effect. Don't leave your audience guessing. 2. Map your lanes to specific subsystems. 3. Always call out cross-lane mitigations. This is an absolute pro tip right here. Sometimes, a tiny, elegant change in downstream consensus behavior completely removes the need for a massive, expensive data management rework upstream. Pointing that out, it makes you look like an engineering genius. And 4, provide a clear locus for investment. This is the ultimate conclusion stakeholders are begging for. Tell them exactly where to put their engineering hours and dollars. When your pitch checks all these boxes, they don't just see raw data. They see a completely transparent, evidence-backed roadmap for the Validators architecture. As you prepare to synthesize your own validator metrics and craft your efficiency narrative, I'll leave you with this critical question to ask yourself. Look at your proposed changes. Are your data and consensus lanes working together, or are you just engineering a more expensive traffic jam? Because as FireDancer continues to evolve, the data traffic on these lanes is only going to get heavier, and the engineers who can properly synthesize this information will be the ones steering the ship. Keep the 2-lane pipeline in mind, use your heuristics, and make sure every optimization actually moves the needle. Thanks for joining me in this explainer. Now go out there and optimize your pipeline.